Hi everyone, my name is Zidong Zhen. I'm very glad to introduce our work, Pedestrian Alignment Network for Large-Scale Person Re-Identification, which has been published on T-CSVT in 2019. This is a joint work with Dr. Liang Zhen and Professor Yi Yang. I will introduce our work from the problem background to the conclusion and academic impacts. Person re-identification (RID) is to find the person of interest from different camera views. The emergency of this task can be attributed to the increasing demand of public safety and the widespread large camera networks in public space. As shown in the image, given one query image from camera 1, we intend to find the person from a large candidate pool collected in other cameras. Different viewpoints of the non-overlapping cameras introduce large appearance changes, which is challenging to the conventional vision algorithm. Most existing methods deploy the deeply learned models and focus on the two different aspects to improve the performance. One line of works intends to leverage the structure information of the human bodies. For instance, the pulse-driven CNN utilized the extra key point detector to help the path detection. In contrast, ECCV-18 works propose to align the feature within the network. Another line of works intends to mine the discriminative semantic information to supervise the network learning, including discriminative losses and human attributes. In this paper, we take one different view and focus on investigating a subtle but important problem. Is important in this pedestrian image good for training? In practice, person ID usually adopt automatic detectors to obtain cropped pedestrian images. As shown in the figure, this process suffers from two types of detector errors: excessive background and path missing. Both errors harm the quality of pedestrian alignment and may compromise pedestrian matching due to the position and scale variance. In this paper, we propose the Pedestrian Alignment Network (PAN), which simultaneously aligns pedestrians within images and learns pedestrian descriptors. It addresses the misdetection problem and the representation learning together and improves the person ID accuracy without extra annotations. As shown in the figure, pedestrian alignment and re-identification are two interconnected problems. When we have identity label of pedestrian bounding box, we are able to find the optimal affine transformation that contains the most information, visual clues, to discriminate different identities. With affine transformation, pedestrians can be better aligned. Furthermore, with superior alignment, more discriminative features can be learned, and the pedestrian matching accuracy can in turn be improved. So these two tasks help each other. In particular, the architecture of the pedestrian alignment network PAN, it consists of two identity networks, base branch, alignment branch, and an affine estimation network. In particular, the base branch predicts the identity from the original image. We use the high-level feature maps of the base branch REST4 feature maps to predict the grid by affine estimation network. Then the grid is applied to the low-level feature maps REST2 feature maps to relocate the object. The alignment branch then receives the aligned feature maps to identify the person again. Note that we do not perform alignment on the original images, as previously done in most existing works, but directly contact on the feature maps to realign the object. In the training phase, the model minimizes two identification losses. In the test phase, we concatenate the two FC features to form a pedestrian descriptor for retrieval. We compare our method with the state-of-the-art methods on three large-scale ReID benchmarks, including Market, CUHK03, and Duke MTMC ReID. Despite the visual difference among these three datasets, such as seeing variance and detection biases, we show that our method consistently improved the retrieval performance. As mentioned, the two descriptors capture the different pedestrian characterism uh, from the original image and the allied feature maps. The results are summarized in the table. We can observe 2 points. First, alignment branch works well on the dataset with more detection noise, such as CUHK and Duke MTMC. Second, there is a consistent improvement on the three datasets when we concatenate the two features. Base branch and alignment branch are complementary. We also study the sensitivity of the person-ready accuracy to the hyperparameter alpha, which is the weight of the two branches. We generally set alpha equals to 0.5. If we do not follow the distribution of the dataset, it is a simple and straightforward choice for the alpha. We further visualize the aligned images. We observe that the network does not perform perfect alignment as the human, but we have to note that it more or less reduces the scale and the position variance, which is critical for the network to learn better representations. No extra location annotations are needed in our network. In a summary, since publication in 2018, the paper reported about 5% improvement in rank 1 accuracy over the state-of-the-art methods on three benchmarks. After that, the proposed system has become a must-be compared one in the community, and the idea of end-to-end alignment has been applied to, to many highest performing object identification systems. This paper has been cited for about 290 times according to the Google Scholar. Besides, the winning solution of the AICT challenge, in conjunction with CVPR 2020, used a mostly identical module as this paper, which outperformed the second best team by a larger margin, about 6% in mean average precision. We hope this work can pave the way for the future studies in object alignment and representation learning. Thanks a lot for your attention. Our code is available at GitHub. You are welcome to check out our paper and code. Thanks.